तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
That E is some kind of thermodynamic potential which is a function of the independent variables S, V and N. This was the energy representation. Now I have written down the first two laws of thermodynamics here. And of course the moment you say that E is a state function which depends on the values of these variables S, V and N, then this at once implies, for instance, that T is equal to delta E over delta S, keeping V and N constant. The pressure P, this coefficient is minus delta E over delta V, keeping S and N constant, and similarly mu is delta E over delta N, keeping S and V constant. So these are standard thermodynamic relations. It tells us that these coefficients here, the integrating factors really are these partial derivatives of E with respect to S, V and N. So this much is obvious from elementary calculus. Okay. Now the physical input comes in when you start asking what is the significance of various partial derivatives and derivatives of those and so on, and it depends on what you would like to call control variables. It is not very convenient to call S a control variable. It is not easy to control the S in a system. It is easier to control E, for instance. So one starts doing a set of Legendre transformations. Now this quantity here is the internal energy of the system and an example of a thermodynamic potential. The reason the word potential is used is because if I take its derivatives with respect to variables S, V and N, the independent variables, then I get other physical quantities here. So in that sense, anything which you differentiate to get other quantities from our mechanical analogy where you differentiate the potential with respect to coordinates to get the force, in the same sense if you take derivatives here of this thermodynamic potential, you end up with various physical quantities. So this much is elementary thermodynamics here, but you need further inputs to make progress, and one of them is the following. You also must assume that you are in the so called thermodynamic limit of statistical mechanics. In other words, the limit in which the volume tends to infinity, the number of particles tends to infinity, and then the ratio of the volume to the number of particles to the volume is some density, it is fixed, that is an intensive quantity. So one would like to proceed to this thermodynamic limit, and in that limit the assumption is in thermodynamics that these extensive quantities, these quantities which increase with the system size, they lead to this E here, and you make a further assumption that this E is a homogeneous function of these variables. So the assumption is that E is a homogeneous function of the extensive variable S, V and N. So you increase those variables in some proportion, then E increases, and further of degree 1. This is based on our experience that the total energy increases with the number of particles linearly and not like the square or the cube or something like that. The moment this assumption is made that it is a homogeneous function of these guys, then of course Elementary calculus gives you Euler's theorem, tells you remember Euler's theorem, it says if you have a function f of x, y, z, etc., which is a homogeneous function of some degree r, then it says that x delta f over delta x plus y delta f over delta y plus etc. is equal to r times f if it is a homogeneous function of degree r. Or another way of saying it is that this is a homogeneous function of degree r if f of lambda x, lambda y, lambda z dot dot dot, where lambda is some constant, you change all these variables, you scale them up by some lambda, and this is equal to lambda to the power r f of x, y, z, etc. This is what is meant by homogeneous function. For example, x squared plus xy plus y squared is a homogeneous function of degree 2, because you scale up x, you scale up y, you get a lambda squared coming out constant. There is a generalization of that concept which we will talk about. You could scale up x in one way like lambda to the power alpha 1, you could scale up y by lambda to the alpha 2 and so on. You could scale each one of them by a different scale variable, and then of course there is a generalized homogeneous relation, the analog of Euler's relation, which we will talk about later on when we need it. But if you assume that E is a homogeneous function of degree 1, then it immediately follows from elementary calculus, from Euler's theorem, that this assumption immediately says that E is equal to S delta E over delta S at V and N plus V delta E over delta V at S and N plus mu N delta E over delta N at S and V, constant S and V. Of degree 1, so it is E to the power 1 here, sitting here. But then if you substitute for what goes on here, we know that delta E over delta S is T, so this is equal to Ts, and this is minus PV, and this is plus mu N, because this quantity is mu. This relation is called the Euler relation. Please notice that you made a further physical input here. Thermodynamics gives you only, the laws of thermodynamics give you only increments. It tells you what is dE, that is it. It does not tell you what E is in absolute terms, but this extra assumption, this assumption of homogeneity of degree 1, that immediately tells you that E itself must be equal to this. These are not increments, so it is actually giving you an extra input, and you have to check against statistical mechanics whether this is really true or not. But if this is true, then look at what happens. It immediately, incidentally, this also tells you that this implies that E plus PV, E minus Ts plus PV is equal to mu N. But what is E minus Ts plus PV? It is the Gibbs free energy, because if you go back here and do various Legendre transforms, which I will do in a minute, you can look at different independent variables here, and the Gibbs free energy is in fact defined as the free energy or the potential when you have as control variables P, T and N instead of S, V and N. So this is also equal to G, and that gives you an interpretation of mu, the chemical potential. This immediately implies mu is equal to G over N, equal to Gibbs free energy per particle. So that is an interesting, is a simple way of remembering what the physical meaning of this chemical potential is. It is in fact the Gibbs free energy per particle, and we will see when we talk about phase transitions that if you take a beaker of water and you boil it in this room, then at the surface the pressure is 1 atmosphere, and that is the same in the liquid phase or in the gas phase, exactly 1 atmosphere, and it's clear that when you have a situation of boiling, when the two phases coexist in thermal equilibrium, it must be energetically as easy to put it in one phase as in the other. It must cost exactly the same energy to put it either in the liquid phase or in the vapor phase. What is the meaning of that? It means that the chemical potentials are exactly the same. That is the reason why in the case of phase equilibrium you insist that the chemical potentials be the same in the two phases, because generally these phase transitions occur at constant pressure and a given temperature. If you change those conditions, then of course it is some other condition, but if you took water and just boiled it freely in the atmosphere, it is the pressures that are the same, and therefore the chemical potentials are the same. So there are other things that the chemical potential is also equal to this. It is the rate of change of the internal energy with the number of particles at fixed entropy and volume, but this is not a directly experimentally accessible thing, unlike this, which tells you immediately what this relation is. Now what is the consequence of this immediately? It says, since E is equal to this, we could ask what is dE, and that is equal to Tds minus Pdv plus mu dN. I differentiate all these guys here, but then there are extra terms, plus S dt minus V dP plus N d mu. So that is the total dE. On the other hand, the laws of thermodynamics tell you that is equal to that. So if you put that in, you get a relation which says that d mu is equal to V over N dP minus S over N dt. It says this is 0, this set of quantities, this sum here is 0, which you can write as d mu is this, or V over N is the volume per particle, the specific volume, little v. So little v dP minus little s dt, and this is the specific volume, and that is the specific entropy. The entropy per particle and the volume per particle, they are intensive quantities because you divide it by the number of particles. And what does that relation tell you in its turn? It says that the chemical potential of a system is a function of this kind of system is a function of its pressure and temperature alone, because d mu is a linear combination of dP and dt. So it says that once you know the pressure and temperature, you know the chemical potential. Okay. This relation here is called the Gibbs Duhem relation, this thing here. D mu is V dP minus S dt. Okay. What is the Gibbs Duhem relation in a more general context? Notice that I wrote this, if I include TdS also as part of a force and a flux, if I call T a generalized force and S the corresponding generalized flux, then you can see that what is happening is that you end up with a relation which says, loosely speaking, if dE equal to summation Fi dxi, including this also inside it, put it inside there, call that one more force and flux, then that is the set of laws of thermodynamics, and the homogeneity argument tells you that E equal to summation I Fi xi, and this immediately implies that summation xi dFi must be equal to 0. So the fluxes times the increments in the generalized forces, that must be equal to 0. That is the generalized Gibbs-Duhem relation. Which arose as a consequence of our homogeneity assumption. If that breaks down, then of course this is not true. There are systems where this is not true, where the energy may increase like not the power like n, but n to a higher power than 1, and then of course such systems you do not have this extensivity property and normal conventional thermodynamics would not be valid, you would have to make modifications. This could happen for instance if you have gravitational force, then if you have a sufficient number of particles there could be collapse, they could all in their own field attract each other and fall in, and you may not have stable thermal equilibrium in such a situation. But apart from those exotic situations, in most normal cases this is what happens. Although I did this in the language of a single component fluid, here you can generalize this in this fashion here, the whole thing is susceptible to generalization. Now what are these Legendre transforms we talked about? Well, let us write those potentials down. So we have E as a function of S, V and N, and from here I do a Legendre transform to a function H of S, P and N, and what must that be? This must be, recall that dE equal to TdS minus PdV plus mu dN for our standard thermodynamic system. Therefore this here is E plus PV, because if I add a plus PV to it, then if I do a dH, this PdV cancels and you end up with a minus VdP, and therefore what is left is a thermodynamic potential in which the control variables are S, P and N. What do you call this quantity? It is called the enthalpy, it is the enthalpy. Chemical engineers are very fond of enthalpy because it is easier for them to control P. Okay. So in the theory of heat engines you constantly talk about the enthalpy, but it is just a Legendre transform from the internal energy. You could also go from here to a function f of T, V and N, and that must be formed by taking E and subtracting the portion here, so E minus Ts. Now what do you call this quantity? The Helmholtz free energy. Okay. Well, you could make another Legendre transform and go to T G of T, P and N, which would be equal to E minus Ts plus PV, and this of course is the Gibbs free energy. These are the four standard thermodynamic potentials: the internal energy, the enthalpy, the Helmholtz free energy and the Gibbs free energy. But you could make other transformations. For instance, you could go from this thing, you could make a transformation, and let us say we have E, instead of that I would like to have S, V and mu instead of N, and since you had a mu N here, this must be equal to E minus mu N, this fashion, and that is the thermodynamic potential. So let me call it some phi 1. You could make another transform, you could go also to a phi 2, instead of S, V and mu I could have S, P and mu. So it is this equal to E plus PV minus mu N, and so on. And you could have yet one more, which would be let us see, TV and mu. So you could have TV and mu, so you could make another transform which goes to a function phi of T, V and mu, and that is equal to E minus Ts plus mu n minus mu N. Incidentally, if you go back here, E minus Ts minus mu N is in fact minus PV, so just minus PV. This is also equal to minus PV. and this is also sometimes used. This is called the grand potential. The reason is it is connected to the grand canonical ensemble in statistical mechanics, whereas these guys are connected to the canonical ensemble where you replaced S and you used T instead. Now you even replaced N and used mu instead, and this is called the grand potential here. So for everything that you get in statistical mechanics there is a corresponding analog in thermodynamics, there has to be, and this is a sort of, these are all the potentials that you would use. But you notice one feature here, notice that in our separation into forces and fluxes we always discovered in a relation like this, for example, we discovered that these quantities occur in thermodynamically conjugate pairs. In some sense one of them is the cause and the other is the response, or the stimulus and the response. Which one you use as the stimulus, which you use as the response is a little shaky, but the fact is, not very unambiguous, but the fact is this and this are extensive variables, and I will call them field variables or state variables. On the other hand this quantity and that quantity are intensive quantities, and I will call them field variables. So we can classify all thermodynamic quantities into field and field variables and state variables. These guys generally are extensive and these are intensive. You can form other intensive quantities from the various state variables, but this thing here is T and that is S, this is P, that is V, this is mu, that is N. You can add to this list, you could in general say stress and strain, and the stress is a tensor, so this is some sigma ij and this is epsilon ij here, right, in this fashion. Then this could be the electric field which you apply on a system, and here would be a polarization, the medium gets polarized, or a magnetic field that you apply on the system and the response is the magnetization on the other side, and so on. You can make things much more complicated, so you can generalize thermodynamics for very complex systems by proceeding along these lines here and using as your postulate a relation, the Gibbs-Duhem type relation plus this relation that dE is equal to a generalized Fi dxi kind of product, and there is a very extensive literature on this, the way thermodynamics is generalized, but in a nutshell this is what it does. But there is one more thing, let us look at, for example, let us look at what the consequences of this would be. So F and G are the most useful in practice, so let us write what is dF. dF is equal to dE, that is TdS minus PdV plus mu dN, that is dE, minus TdS minus S dt. So you are left with minus S dt up here, and similarly let us also write what dG is. dG equal to, so you are going to have a minus S dt from here, and then you added a plus V PV, so this becomes a plus V dP plus mu dN. Okay. Let us just look at these two relations. Now this immediately tells you, playing with a little bit of partial derivatives, this tells you that S is delta F over delta T with a minus sign, S equal to minus this at constant V and N, but it is also equal to, S is also equal to minus delta G over delta T at constant P and N, and these must be equal to each other identically, it is the same quantity. You further have, so let us write this out, V is delta G over delta P at constant t and n. Very important to keep track of what is kept constant in the partial derivatives, and similarly mu is delta g over delta n at constant p and t. That is not too surprising. That's not too surprising because we already know that mu is g over n itself and it is a function of p and t. So if you are keeping p and t constant, then it is immediately clear that mu is also the partial derivatives with these two constants. So this is in exact correspondence with what we have already proved there. Now what are the relations here? This says p is delta f over delta v at constant t and n with a minus sign, and mu can also be written as delta f over delta n at constant t and v. Now that is a very important relation because it says that the chemical potential is also the rate of change of the free energy with respect to the number of particles at constant t and v. A little later, maybe give this as an exercise, you can also show that if I define this little f as the f over n, free energy per particle, and instead of n here I talk about the density, the number of particles per unit volume, then you can also rewrite this as the partial derivative of the free energy per particle divided with respect to the density. So that is another useful relation here. But now what does this mean? It says these thermodynamic potentials, their first derivatives with respect to the independent variables on which they depend are other thermodynamic variables. So that is exactly what has happened. In fact, you recovered the field variables by differentiating the potentials with respect to the various state variables and vice versa. Okay. So you recover thermodynamic pairs in this fashion. Now what happens if you differentiate a second time? What are the second derivatives of these potentials? What do they physically represent? For instance, if I differentiated f a second time with respect to t, what would happen? Remember the law that we have, namely dq, this is t ds, this is equal to dE plus p dV minus mu dN, which I rewrote in many different ways. If you are at constant v and n, then dq over dt at constant v and n, what do you call this? What do you call this? It is the specific heat. It is the rate at which heat is absorbed. I mean, how much heat you must supply to change the temperature by a given amount at constant v and n. By definition, this is equal to Cv by definition. So this by definition is equal to T delta S over delta T at constant v and n by definition. Of course Cv is also equal to dE over dt because v and n are kept constant, so these two go away in this case. So this is your definition of the specific heat. If I put that in here, this relation, it says that Cv equal to T delta S over delta T at constant v and n, but S itself is this quantity here at constant v and n, so this is equal to minus T delta 2F over delta T2 at v and n. In other words, response functions are second derivatives of thermodynamic potentials. First derivatives are other thermodynamic variables, but the second derivatives are quantities like the response function Cv. This tells you what is the efficiency with which the system can absorb energy and change its temperature. It also tells you something very crucial. Cv cannot be negative. That is thermodynamic stability implies that in a state of thermal equilibrium at constant Tv and n, this quantity F is at an absolute minimum, which means its second derivatives must have specific signs, and one of those conditions, stability conditions, leads to the fact that Cv, this quantity here, must be positive. That means this quantity must be negative, d2F over dt2 must be negative, and that says specific convexity properties of F as a function of T. So this is called thermodynamic stability. It is also called Le Chatelier's principle. That is nothing but a word for thermodynamic stability, and it essentially says that these potentials are at minima correspond to the equilibrium states. So this is an example of such a relation, that the second derivative is a response function here. We can derive exactly the same thing here. What Cp? Cp is equal to T delta S over delta T at constant pressure and N, but at constant pressure and N you have delta G here sitting for you, so this is equal to minus T delta 2G over delta T2 at constant P and N. Okay. And of course you can show that Cp must be greater than Cv. I am going to give all these thermodynamic identities as exercises. It is not very hard to show that this quantity is in fact bigger than this quantity and this quantity is bigger than 0 for thermodynamic stability. But again, second derivative implies certain convexity properties here. What is the isothermal compressibility? How do you define the isothermal compressibility of a gas? KT equal to at constant temperature and a fixed number of particles, so let us call it Kt comma n, T comma n. This is equal to the volumetric strain over the change in the pressure, right. So this is equal to minus 1 over V delta V over delta P at constant T and N. That is the isothermal compressibility. We could have an adiabatic compressibility where you have S constant instead of N, but let us look at the isothermal compressibility. It is this quantity, and I need the minus sign because, as you know, in the generalized force law F dx, it is minus P dV that appears, because if I increase P the volume shrinks. So I take that into account with that minus sign there, and then this is, so it tells you correctly what the work done is, and this is the definition of the isothermal compressibility. Now can we write this in terms of these relations here? Yes indeed, because delta V over delta P would be the second derivative here. So you could also write this as equal to minus 1 over V delta 2G over delta P2 at constant T and N. Again the positivity of this quantity here, if you increase the volume, if you increase the pressure, the volume must decrease rather than increase, and so on. In some directions the thing could expand actually if it has a negative Poisson ratio, but if you use hydrostatic pressure things must decrease, that is stability. Are you familiar with the Poisson ratio? Yes? Are there any limits on the Poisson ratio? It can't exceed a half. And what about, can it be negative? Is it positive? You don't know if it, you see what is Poisson ratio? Okay, for those who have forgotten, that is being charitable. If I take a piece of material like this and I pull it in this direction, then it could contract in the transverse directions, right. Overall there would be extension in this direction, there would be possibly contraction in the other direction, and the ratio of that contraction strain to the extension strain is called Poisson's ratio, right. On the other hand, if the Poisson ratio is negative, it means that if I pull in this direction it also expands in this direction as well. What we do know for stability, and this is not very hard to prove, if you look at the total change in volume, it is easy to see that this ratio nu, Poisson ratio, must be less than a half in absolute terms, can't be bigger than half, otherwise thermodynamic stability is violated. But the question is, can it be negative? If I pull in this direction, will it also blow up in this direction? Is this positive? Is this possible? It is theoretically possible. Is it possible in practice? There are materials. Tell me one. Tell me one. Here is a loose analogy. Who can spare a sheet of paper? Who can spare a sheet of paper? Don't tear notebooks. I feel bad about this. Here is a sheet of paper. I hope it is a notice from administration so we can see it. So, okay. I crumple it up in this fashion. Imagine this is a sort of composite material like a network material of some kind. You have to use your imagination, but look at what happens to its side. So you see it expands in the other direction too. And it's happening because it's a sort of network kind of object, it's a very crude model of it. So it's possible to have a Poisson ratio that's negative, but it can't be more negative than -1. So it runs from -1 to +½ and what is it for most materials, most metals, normal stuff? About 0.25, 0.3, something like that, right. So that's the order of magnitude of this quantity. Now the compressibility on the other hand, the isothermal compressibility must always be positive, and it's a relation of this kind. We could write down, this is incidentally, how is this related to the bulk modulus? It's the inverse of the bulk modulus, it's the reciprocal of the bulk modulus, right. Give me an experiment where people measure this compressibility. Pardon me? How many of you have cycles? Everybody has a cycle, okay. How does the guy who fills tire, that little boy, that poor urchin, how does he test whether you have enough pressure or not? Well, he kicks the tire, right, or he presses it. What's he actually doing? How is he getting information about the pressure? By kicking it. By kicking it he finds out how rigid it is. So he is really measuring the compressibility of this object, but how come he is finding the pressure by doing that? Practical thermodynamics, come on, you are all engineers who are going to send a mission to the moon. How does he do that? Let's go and let's work this out. We need to work out all these things. Let's work this out. What does that poor kid outside the central school do when he kicks your tire? So we would like to calculate this quantity, -1/v delta V over delta P. So let's do that for an ideal gas. You have PV equal to nRT for an ideal gas, huh? So V equal to nRT over P, and now let's compute for a fixed number of particles. Let's compute delta V over delta P at constant T and N. This is equal to minus nRT over P squared. So K, T and N equal to -1/V, minus signs cancel, so it's 1/V, and 1/V is P over nRT multiplied by nRT over P squared, which is equal to 1/P. So you see, the bulk modulus is the pressure. Now the compressibility is indeed the pressure. If it is very compressible, the pressure is low, but if it is not compressible, the compressibility is low, it is a very rigid object, the pressure is high. So that poor guy actually knows this, and that is the reason why he kicks the tire, in order to find out what the pressure is, although he is measuring the compressibility. It is directly related to this. I leave it as an exercise to you to find out what will happen if the process is adiabatic. You might actually say, this guy is pumping the air quite fast, so you can't say the temperature is constant because it does get heated up. But if the process is sufficiently fast, adiabatic, then what happens? Constant entropy process rather than constant temperature, not isothermal. What would happen? What would this be? You already know the answer, it's just that you are not relating this. S and N. In this ideal gas, what do you think it will be? Gamma P. Very good, it's 1/gamma P. You know Newton's formula for the velocity of sound in a gas, it's square root of P over rho, but then Newton pointed out that this is really an adiabatic process because the stress waves propagate quite, the rarefaction and so on is not an isothermal process, and therefore much better approximations in adiabatic process, and then the formula is square root of gamma P over rho. So all that's happened is that P is replaced by gamma P here, this thing here. I leave you to find out what it is for a van der Waals gas, where you have actually included the attraction between particles at long distances. What is the van der Waals equation of state? This is important, it is not, this is important. P plus A over V squared times V minus B equal to nRT. So it is a crude approximation to what happens in gases. You say that the volume V is replaced by an effective volume V minus B because these particles occupy some space, so to speak. Actually that is not really true, we will see what it is in a minute, and then you have a term which says that the pressure is actually reduced a little bit, it is not the original pressure. So you should really rewrite this equation as P equal to nRT over V minus B minus A over V squared. That is the way to write it. You write the pressure as a function of the temperature and the volume. That is called the equation of state of the system. Now compared to the ideal gas, you did not have this term and you have a V here instead of V minus B. So what has happened is that the volume has effectively reduced by a certain amount, and this is because these particles are supposed to have finite volume. That is not strictly true, we will see what it really means. And the other term minus A over V squared says that the pressure is less than what it would normally be. What is the physical reason for that? Attraction between particles. So there is not as much force on the walls. You put in an external wall or something and ask what is the force per unit area, there is some attraction between the particles, and that is 1 over V squared. Now what really happens is that if you plot the potential seen by a particle due to another particle at a distance r from it, this intermolecular potential has a very generic shape independent of various other factors, and it is something like this potential. So this portion of it, this portion of this potential, and then here is a minimum. So till the minimum dV over dr here is negative, so minus dV over dr is positive, in other words particles are pushed away. So it is hardcore repulsion of some kind at short distances, and at long distances there is an attraction. So that is the origin of this intermolecular potential. This is a very crude origin. This portion of it, this region here corresponds to repulsive force, and this portion corresponds to an attractive force at long distances. What is the repulsive force due to in real life? Due to actual molecules. These are not spheres or anything, they are not billiard balls and so on. What do you think is this repulsive force is due to essentially? Pardon me? The nucleus is very unlikely, because it is very unlikely, because the nucleus is 10 to the minus 15 meters and the atom or molecule size is of the order of 10 to the minus 10 meters or some multiple of 10 to the minus 10 meters. So 5 orders of magnitude, the chance that two nuclei will actually hit each other in a gas is very small. The Pauli exclusion principle, really, not even the electron repulsion, the Pauli exclusion principle. The fact that you cannot put two electrons in the same state at the same time, no two electrons in the universe can be in the same state at the same time, causes this repulsion. So a large contribution to that is this shape of the potential here is due to the Pauli exclusion principle. So it is very quantum mechanical in origin, and that is the reason why it is very difficult to model, and it is very molecule dependent. And the standard molecular physics approximation for closed shell for inert gases, for example, would be something called a 612 potential. So the first portion goes like a 1 over r to the power 12, some very high power as r goes to 0, and the long range attractive potential goes like 1 over r to the power 6 with a minus sign. What is the origin of this attractive force? Where does this come from? So this 612 potential which also is called the Lennard-Jones potential is of the form V of r is equal to some constant V naught times some a over r to the power 12 minus a over r to the power 6, and this minimum here is at some multiple of a, 2 to the 1/6 times a or something like that. Okay, so there is a scale factor a, and then there is minimum here. This is proportional to V naught minus 4 V naught or something like that. okay. So this thing here is the general Lennard-Jones form. This portion is the repulsive part, leads to the repulsive force, and that leads to the long range attractive force. This is strictly an empirical model here. It could be 18, it could be e to the power whatever minus 1 over r and so on, but the fact is that this is a completely quantum effect at this stage, hard to model in exact terms. The other term, the attractive portion, is more empirically modeled more easily. Where does it come from? Where does this r to the 6 come from? It's a very simple physical explanation for the 6. It's dipole interaction, because after all if you took two neutral atoms and they are completely spherically symmetrical, there should be no force at all, no electrostatic force at all. So if I took two neutral atoms, I have an atom here and an atom there, and this is a plus charge and this is a minus cloud around it, this is plus, this is all minus around it. If each of them is spherically symmetrical, then there is no force outside, there is no field outside completely for these neutral atoms if the charge distribution is spherically symmetrical. But the fact is that these are actually dynamic entities, they are changing all the time and there are fluctuations. So instantaneous fluctuations can cause a dipole moment here. If momentarily this shifts from the center of attractions here, there could be a dipole moment here, and if there is a similar dipole moment there, then there is a dipole-dipole interaction. Now what happens is that a dipole moment here, if there is a dipole moment P1, electric dipole moment, it causes an electric field at the other end there, and what does the energy go like? The energy, potential energy U, goes like P dot E. This is what the energy is going to be. If you put a dipole of moment P in an electric field E, it goes like P dot E, right? But this polarization of this molecule, this E is due to the dipole moment here, and what does that E go like? It goes like 1 over r cubed, because a monopole field will go like 1 over r squared, the potential goes like 1 over r, the field goes like 1 over r squared. A dipole field, the potential goes like 1 over r squared, the field goes like 1 over r cubed. But the greater the field here, the greater the separation here. So this P itself is some alpha times E, where alpha is the polarizability. So the whole potential energy U goes like E squared, and that goes like 1 over r to the power 6, 1 over r cubed squared. So this is the simple explanation of where this thing comes from. It is called the van der Waals force. There are more complicated explanations, detailed explanations or theories possible, but this is the origin of it, this is where it comes from. Now what is the assumption I made here? I made the assumption that these do not have permanent dipoles, these guys actually are spherically symmetric charge distributions, and it is only the induced dipole effect that I have looked at. If these molecules had permanent dipole moments, then this is not the answer. Water molecules would not attract each other with this kind of force. Water has got a permanent electric dipole moment. Then what do you think the answer is? Yeah, 1 by r cubed. It is P1 dot P2 over r cubed, and P1 and P2 are the permanent dipole moments divided by r cubed. So the force will go like a 1 over r to the 4 in that case. Lots of the anomalous properties of water are actually traceable to the fact that it has got a permanent electric dipole moment. Many anomalous properties. In fact, water is the most anomalous substance known. Almost every property of it is anomalous. It is not a simple thing to explain, it has very complex behavior, and even the number of phases of water is not fully understood yet. So it has all kinds of crazy things, and all these things go out of the window, but this is the origin of the van der Waals. Now coming back here, how does this mimic the 1 over r6? Where does that come from? Why should it be 1 over v squared and not anything else? And the idea has to do with, we are going to discuss this when we do phase transitions, it has to do with what is called mean field theory. It says you have all these molecules and you are trying to find out the correction to the pressure, which is the energy density pressure has the same dimensions as the energy per unit volume, and you are trying to find out the correction to this energy density from the attractive force between the molecules. And the idea is any one of these guys is going to be affected by all of them around, right, and if you assume in the simplest approximation that they are affected equally by all of them around, everyone is affected by everybody else in exactly the same fashion independent of the distance, then this has each of them, each molecule has an energy proportional to the concentration of particles n, and there are n of them per unit volume, so the whole energy goes like n squared, and that is like n squared over v squared, and you have hidden the n squared in the parameter a and taken only the v squared down. So that is how van der Waals came out with this 1 over v squared, and today we understand the van der Waals equation of state as what is called a mean field approximation, and we are going to do that in some detail in statistical physics when we do phase transitions. But the van der Waals equation of state is an example of a mean field theory of a fluid in which an attractive force is included. This is of course completely empirical. So what this van der Waals does is to say that this complicated interatomic intermolecular potential is approximated by saying that there is a hard core repulsion where the potential is infinite, and then there is a 1 over R6 attraction. So that is an approximation to the true intermolecular force, and in that approximation you can start with statistical mechanics, put in this interaction, put in this approximate potential, etc., and then after a lot of jugglery you end up with a van der Waals equation of state, which is completely empirical. Deriving it is non-trivial, there is no single rigorous derivation for it, there is no universal equation of state for gases. This is what the people were searching for in the 19th century before they realized that this is an intrinsically quantum mechanical effect. It depends on the molecular species, it depends on what kind of system you have. Therefore apart from situations near phase transitions, near critical points, everywhere else systems are very specific to themselves, there is no universal equation of state. But this was a holy grail in the 19th century to try to find the correct equation of state. Today we know that what statistical mechanics will tell you is that the pressure is equal to nRT, P equal to nRT over V times a power series 1 plus higher order terms, this is called the Virial expansion, and all these terms would have coefficients that depend on the temperature divided by increasing powers of V in the denominator, V squared, V cubed, V4 and so on. And the van der Waals is a very special case of it in which all these virial coefficients degenerated and put into one parameter here, because there is already a 1 over V squared, and if I expand this binomially in inverse powers of V, then you will see that all the coefficients are just powers of B up on top. So it is a very degenerate case in that sense. So good to know where the phenomenology of the 19th century stands when you do statistical mechanics, but it was a very great insight, it was very important, very important development in the theory of condensed matter itself. Van der Waals' thesis was on this problem, and it was so important that Maxwell learnt Dutch in order to be able to read van der Waals' thesis in the original. He regarded this as a very important piece of work, and since he was one of the founders of statistical mechanics, he thought it is important to know this, and it's great inputs here. Okay, so let us come back here. We were talking about second derivatives. The last thing I want to ask is, what happens if you took cross derivatives? We have said second derivatives of thermodynamic potentials lead to response functions like the specific heat, etc. What would be cross derivatives? I differentiate with respect to temperature and volume, for instance, etc. What would they correspond to? I leave it as an exercise to you to show that there are other response functions. For example, what is the isothermal coefficient, what is the coefficient of linear expansion, thermal expansion, the coefficient of thermal expansion, the rate at which the volume changes with respect to the temperature. So compute that number, and then you discover it is a mixed derivative, one with respect to t, one with respect to v, and so on. So they too are response functions, and since we know that stability will involve, when you have functions of two variables for example, stability will involve an absolute minimum of a function of x and y, means that delta 2f over delta x2 is positive, delta 2f over delta y2 is positive, and the product of these two must be greater than delta 2f over delta x delta y the whole squared. So there are other stability conditions that come in from imposing the requirement of stable thermal equilibrium. So this is roughly what we are. The only thing I did not do was Maxwell relations, and I leave you to figure out, I will give it as a problem set. Each of these things, each of these relations, each time you write a thermodynamic potential as a function of 3 variables, you have 3 Maxwell equations, because you can differentiate this with respect to T and then P, or P and then T, and equate the two, and you get a Maxwell relation. And for each of them you are going to get 3 relations. Since there are 6 thermodynamic potentials we have looked at, there are going to be 18 Maxwell relations. Write them down. Normally you keep n fixed, in which case it will reduce to just 4 Maxwell relations, but otherwise you have a very large number of them. Okay. So that is thermodynamics in a nutshell, and the rest will be in a problem sheet. Okay.